and I'll give you the guidelines to sketch the graph of a given function, okay? And so I'm going to explain the steps or all the guidelines by going over one example in details. So the example that I have in mind is the following. So let's say I have the function f of x. Okay, f of x is the function x squared over the root of x squared plus 1. Oops, sorry, root of x plus 1. Root of x plus 1. Okay, so what we want to do is sketch the graph of this function. Alright, so I'm going to give you the steps to do this. So the very first step would be to determine what's the domain of this function. Okay, so can somebody tell me what is the domain of this function? Yeah. Yeah, why? Yeah, so notice that I have the root of x plus 1 in the denominator, right? Now first of all, because I have x plus 1 in the denominator, then I need x plus 1 to be non-negative, right? But also I don't want it to be 0, because then I'll get a 0 in the denominator. So I want this x plus 1 to be strictly bigger than 0, right? Positive, not non-negative. I want it positive. So that implies that x has to be larger than negative 1. So then what we get is that the domain of this function is everything from negative 1 up to infinity. Is everybody okay with that? Alright, so that's the first step. What's the second step? The second step, I'm going to term it the terminal behavior. Terminal behavior. What do I mean by that? Well, notice that the domain, I want to know what is happening to the function at the extremes points of the domain. So I want to know how the function behaves near negative 1, but on the right side of negative 1, right? Because on the left side of negative 1 there is no graph, right? Because the function is undefined on the left side of negative 1. So I need to know what is happening at negative 1 from the right side to the function. And also I want to know when x goes to infinity, what is happening to the function at. That makes sense? And when you determine that, you are basically also finding out what are the asymptotes, the vertical and the horizontal asymptotes. So you are actually at the same time finding out the horizontal. So this will also tell you if there are any horizontal and vertical asymptotes. Okay, so horizontal and vertical asymptotes. So this will also tell you if there are any horizontal and vertical asymptotes. So let's see how we could decide this. So basically I want to know
Basically, if I want to know how the function behaves near -1, I basically want to know what's the limit. What's the limit as x goes to -1, but from the right side of 1, because it doesn't make sense to ask what happens as x approaches -1 from the right, from the left. And what's the function? The function is x squared over the root of x minus 1. Can someone tell me what that, sorry, x plus 1. Can someone tell me what is this limit? You have to remember what I said about this type of limits. Okay? What is this limit? As x goes to -1, what is happening to x squared? X close to -1, x squared is close to? Close to +1, right? And when x is close to -1, the denominator is close to? 0. So what's the limit of the ratio then? What was my guideline for this? Denominator is approaching 0. Numerator is approaching a non-zero number. The ratio will approach plus or minus infinity, right? Which one is it in this case? Plus, because both numerator and the denominator, they are positive. So when x is near -1, so this would be positive infinity. Okay, so that means I have a vertical asymptote, right? I have a vertical asymptote at where? At x equals to -1, I have a vertical asymptote, right? That's the definition of vertical asymptote. Vertical asymptote means the graph blows up near the asymptote, right? Or down. Okay, now I also want to know what is happening at infinity, right? So I take the limit as x goes to infinity of x squared over x plus 1, root of that. What is this limit? What is this limit? This is a 3.4 question, right? How do you find the limit at infinity here? What's the trick? You factor out the highest order term, right, and see what the limit is. But I also gave you a quick way of determining this type of limits. I said if you're looking at the limit as x goes to infinity and you have just polynomial functions, then the limit is basically determined by the highest order terms, right? So in the denominator, if you ignore the 1, you're left with root x. So then you have x squared over root x. And what is that equal to? X squared over root x means x squared divided by actually half, which means actually 3/2, right? So x goes to infinity, then the limit would be what? Infinity, right? You guys realize that, everybody? So this limit is infinity. This is a 3.4 question, right? So what I see is that I have no horizontal asymptotes, right? No horizontal asymptotes. Is everybody okay with that? I don't have any horizontal asymptote. If this limit was a number, then I will have a horizontal asymptote, right? But we don't. So now we know the terminal behavior. Okay, so that's my second step. Let's see. Okay, so the third step I'm going to do is if you can find the intercepts, go ahead and find the intercepts, okay? So in the third step, If there are any intercepts that you can find, go ahead and find them. So how do you find the y-intercept? Intercept. In order to find the y-intercept, you have to let x to be 0 and find out what's the y value, right? So in my function, if I replace x by 0, what do I get? 0, right? So the y-intercept is at 0, 0, right? And how about the x-intercept? To find the x-intercept, we have to let y to be 0, right? Am I making sense? That is, you let f of x to be 0 and then solve for x, right? So this is the function f of x. If I set this to equal to 0, then I have to solve for x, okay? So in order to find the x-intercept, you set the function to equal 0. You set the function to equal 0 and then solve for x, right? If you solve for x, what do you get? Remember, we set y to be 0, so the y is 0. And if I solve for x, I also get what? 0. So there is only the x and y intercept, because it goes through the origin, the x and y intercepts are the same. Is everybody okay? So there are no more x-intercepts. How many? If I have a function, how many y-intercepts can I get? Can I get more than one y-intercept? No. But can I get more than one x-intercept? Yes. Okay. Good. Okay. So we know the intercepts now. The third step, sorry, this was the third step. The fourth step, what I'm going to do is determine where f is increasing and decreasing, okay? Determine where f is increasing and where f is decreasing. Well, in order to do that, what do I have to do? Remember, my function f of x is x squared over the root of x plus 1, right? In order to find where the function is increasing and decreasing, my first step is what? So I'm going to write step A. I have to find the derivative, right? And if I find the derivative, what do I get? I have to square the denominator, right? And apply the quotient rule. So if I square the denominator, what do I get? The root of x plus 1 squared, so I get x plus 1. And then in the numerator, I will be getting x plus 1 to the half. I'm writing half because the root is just the exponent half, right? And then I have to multiply that by the derivative of the numerator, which is 2x, and subtract x squared with the derivative of the denominator, right? And the derivative of the denominator means the derivative of x plus 1 to the half, right? X plus 1 to the half. What's the derivative of that? Half x plus 1 to the 1 minus half, which is negative half. Sorry, half minus 1, which is negative half. Times 1, yes. Times 1, which I'm not going to write here. Okay, so let's see how can we simplify this. Was that? There are a couple of different ways of simplifying this, but one easy way to simplify this is, because I have that negative exponent there and the fraction half, if you just multiply by 2 times x plus 1 to the half, and also divide by 2 times x plus 1 to the half, okay, if you do that, it's going to simplify a lot. So note in the denominator, then what do I get? When I multiply the two denominators, I get 2 times what? X plus 1 to the 3 half, right? Because it's 1 plus a half. The exponent on x plus 1 is 1. I am multiplying these two denominators. The exponent on this guy is 1, so it's going to be 3 half. Now when I multiply the first term in the first fraction with this guy, with this 2 times x plus 1 to the half, what do I get? I get 2 times 2x, which would be 4x, multiplied by x plus 1, right? So I get 4x times x plus 1. And minus, notice that 2.5 will cancel out. I get just x squared. You agree with that? Because x plus 1 to the negative half and x plus 1 to the half, when we multiply them, they cancel out. And that was our goal, right? We multiplied by this to get rid of that negative exponent. Is everybody okay with that? Yeah. The numerator, I am multiplying this with this. So if you multiply them, you get 2 times 2 is 4. You get 4x. And when you multiply x plus 1 to the half with x plus 1 to the half, you get x plus 1 to the half plus half, right? Which is 1. Right? Okay, so now what do I get? I get 4x squared plus 1 minus x squared, right? So what is that? 3x squared plus 4x divided by 2 times x plus 1 to the 3 half. Okay, so that's the derivative, right? So once I compute the derivative, then I have to find the critical points, right? So the part B would be find the critical points. And how do I compute the critical points? I have to solve f prime of x equals to 0 first. And if f prime of x, so what is f prime of x? Is this, right? So if the derivative is 0, then what should be 0 here? The numerator has to be 0. So I know that 3x squared plus 4x must be 0. And if I factor out x, I get 3x plus 4. So that's going to be 0. Okay, so then I get x is 0, or x is negative 4/3, isn't it? You guys agree with that? If you set 3x plus 4 to 0, then you get 3x to be negative 4, and then x would be negative 4/3. Notice that negative 4/3 is not in the domain, right? Notice that this guy is not in the domain of f, right? Because the domain is up to negative 1, right? On the left. So we basically ignore this then. So then I'm getting only one critical point at x equals to 0. But we also have to solve what? Solve f prime of x does not exist, right? And the derivative doesn't exist where? The derivative doesn't exist for what values of x? Yeah, at -1, or you can say any point beyond -1, because the function is undefined there. But I could say that if I look at the derivative function, the only place where that's undefined is when x is -1, right? However, the -1 is not in the domain, right? The domain is from -1 up to infinity. We already looked at what happens to the right of -1, so we don't have to worry about -1 anymore. Okay, so no solution in the domain. No solution in the domain. Okay, so the only critical point we have then, let me highlight that with a magenta here. So this is the only critical point. Everybody's okay? All right, so now what's the third step for determining where the function is increasing and decreasing? I sketch where the derivative is positive and negative, right? So I make a number line, but I am going to make a number line, and I'm going to only highlight the portion from -1 to infinity, right? So here is -1, let's say. Okay. Oops. Let me make sure that I have a hole here. The domain, the function is undefined at -1, and then the function is defined everywhere else. And let's say 0 is right here. So that's the 0 is the only critical point. That's why I plot 0. Now I have to determine what's the sign of the derivative in each of the two subintervals here. So the critical point will divide your domain into subintervals. So I have the critical, so the domain is from -1 to infinity. I got the critical point here, so it's dividing the domain into two parts. I need to know what's the sign of the derivative on each subinterval. Okay, so what's the sign? How do I determine the sign between -1 and 0? Yeah, so if I go back to my function, the derivative function, which is right here, so for what values of x is this function, is this derivative positive, and for what values of x is this negative? Now notice that if I pick x to be 1, right? 1, it's to the right of 0. If I pick x to be 1, then certainly it's positive, right? And between 0 and 1, if I pick the number half, yeah, it's 4x squared plus, yeah. If I pick the number half, then I still get positive. Did I make a mistake somewhere? I feel like... Oh, why am I plugging in half? Half is to the right of 0, right? I should be plugging in -half, right? Okay, if I plug in -half, I am going to get negative, right? Because it's going to be, yeah, it's going to be negative. Everybody realizes that. If I plug in -half for x in the derivative, I get negative. So I see that the function, the derivative function is negative here, and then the value of the derivative function is positive here. So what does it tell me? It tells me that my function f, then decreases here, and then my function f increases here, right? Is everybody okay with that? Okay. Okay, I have, this is -1 to infinity, that's the domain of the function. I found a critical point, I plot the critical point in the domain, and then the critical point divides the domain, in this case, into two parts. I need to know what's the sign of the derivative function here and here. In order to determine the sign of the derivative function between -1 and 0, you have to choose a point between -1 and 0, like -half, and plug in -half in the formula for f prime. So here is f prime. If I plug in -half here, you'll see that I get a negative quantity. That makes the derivative negative. And if I pick a point to the right of 0, 1, you'll see that the derivative is positive, okay? Okay, so now I know where the function increases and decreases, okay? So what do you think is the next next step? Yeah, so this would be step, was it 5? 5, okay. Okay, so step 5 would be basically determine concavity. Determine concavity. So by that I mean determine where the function is concave upward and where the function is concave downward. And so how do I do that? Well, I have to I have to find what? What's the first step? Find the second derivative. Well, this time what was the denominator in the first derivative? In the first derivative, the denominator is what? In the denominator, I think it was 2 times x plus 1 to the 3/2. So if you square that, what do you get? If you square that, you get the 2 squared would be 4, and then if square of x plus 1 to the 3/2 would be what? X plus 1 to the 3, right? You have x plus 1 to the 3/2, so you have, if you square that, that half goes away, right? Is everybody okay with that? Yeah. Okay. Now, in the numerator, what would I have? I would have 2 times x plus 1 to the 3/2. That's the denominator, right? And then that needs to be multiplied by the derivative of the numerator, which is what? 6x plus 4, and then minus 3x squared plus 4x. That's the numerator now, multiplied by the derivative of the denominator, right? So what's the derivative of the denominator? Anybody?
3.
Yeah, if you take the derivative of the denominator, let me write it out. So what you get is 2 times 3/2 x plus 1 to the 3/2 minus 1, which is half, right? And then multiplied by 1, which is, okay, I can ignore that. Is everybody okay with that? So you get 3 times x plus 1 to the half, as you said. Now, okay, so what I have then is the following. Okay, let me do one thing here, which is, now how would I simplify this? Again, one thing I could do is I can factor out x plus 1 to the half in the numerator, but I could also do the following. Notice that if I multiply the numerator by x plus 1 to the half, then the fractional exponents will go away, right? You guys agree with that? The fractional powers. So if you don't like fractional powers, that's what you should do. So if I do that, if I write x plus 1 to the half, you know what, this time I'm not going to, sorry about that, this time I'm just, because I have to factor out anyway, so I'm just going to factor out x plus 1 to the half this time. So I'm going to factor out x plus 1 to the half. 2 here cancels out, right? 2 cancels out there. If I factor out x plus 1 to the half, in the from the first term, what do I get? What do I get from the first term? 2 times x plus 1 times 6x plus 4. You guys agree with that? Because when I divide x plus 1 to the 3 half by x plus 1 to the half, it will be x plus 1 to the 3 half minus half, which would be 1. And then minus, here all I get is 3 is left, and then also I have 3x squared plus 4x left.
And you delete that 3 right off that?
Yeah, we have to do that, yes. We're going to multiply out everything inside the brackets. 4 times x plus 1 to the 3. Can I combine x plus 1 to the half with x plus 1 cubed in the denominator? What would I get? I would get 4 times x plus 1 to the 3 minus a half, which is what? 5 half. Okay, inside the brackets, if I multiply out, what do I get? What am I going to get? 6x squared, so that's 12x squared plus 6x plus 4x is 10x plus 20x plus 4 times 2, that's 8, minus 9x squared minus 12x. Okay, so what is that? 12x squared minus 9x squared, what is that? 3x squared. 20x minus 12x is what? 20 minus 12 is 8x and plus 8. And I have 4 times x plus 1 to the 3 half. Okay, so we say, oh, 5 half, yes. Does it look like 5 now? Okay. Not that it was 5 before. Okay, so we have the derivative simplified out. What's part B then? Part B would be what? Solve f double prime of x equals to 0. Okay, so what is that? The second derivative is where? This is the second derivative, right? That is my f double prime of x. This second derivative would be 0 when what? 3x squared plus 8x plus 8 would be 0. And I don't think you can factor this out, so go ahead and apply the quadratic formula. So what you're going to get is negative 8 plus or minus the root of 8 squared minus 4 times 3 times 8 divided by 2 times 3, right? And what you're getting then is negative 8 plus or minus the root of negative 32 over 6. So no real solution, right? No real solution. Okay, we now then have to solve f double prime of x does not exist. And again, the only point that you can think of where the second derivative doesn't exist is where the denominator vanishes. And the denominator vanishes at negative 1 only. And negative 1 is not in the domain. So no solution inside the domain. No solution inside the domain. Is everybody okay? So basically I got no critical points here, right? Okay. Well, what's part C then? I find out where the second derivative is go up. So now I have to find out where the second derivative is positive and negative, right? The fact that I didn't get any critical points, what does it tell you? Yeah, it tells you that either the second derivative is positive everywhere or it is negative everywhere. Okay? So since you don't have any critical points, that's what happens. So what I'm going to do is make my domain again. And here is the negative 1 and positive infinity. And what's the sign of the second derivative then? Well, I look at the second derivative. You can plug in whatever you want. But it is clear that if x is larger than negative 1, the numerator is always positive, right? If you want, you can plug in 0, for example. I didn't have any critical points, so I didn't divide the domain at all. So you just pick any point and see what's the sign. So plug in 0, for example, you get 8, so it's positive. So I know that the second derivative is always positive. And positive means what? Concave up. So it is concave up on the entire domain. Is everybody okay with what we did? So we found the asymptotes, we got the terminal behavior done. I think this is enough for us to find out. We found the intercepts and so on, so we can now find, sketch the curve. Now, before I do that, what I want to do is plot the points on the graph corresponding to the critical points and the intercepts. The first step you want to do when you sketch is plot the points. So go ahead and try to do that on your own. Plot the points corresponding to the intercepts and the critical points first, and then we are going to sketch the curve. So the only intercept I had, the only critical point I had was what? What was my critical point? The 0 was the only critical point, and actually I had only one intercept at 0, right? So that is easy enough. So the only point that I am gonna sketch here is that. So let me make my x-intercept, my y-intercept. We know that we have a vertical tangent at -1, right? So I am going to make a vertical tangent at -1. So I don't know, let's say this is my -1, let's say. So this line that I just sketched, that's the line x equals to -1. Okay? So this is where -1 is. And we know, so give 1 point on the graph would be what? 1 point on the graph would be 0, 0, right? That's the point corresponding to the critical point and the intercepts. I have no other intercepts, I have no other critical points. Now, I have to determine what is happening to the left of 0. So where is the function increasing and decreasing? We know that on the left side of 0, right? On the left side of 0, the function decreases and it's concave up, right? So on the left side, the function decreases and concave up. So what do I get? The function decreases and concave up on the left side of 0. So that's what's happening there. And I know that at -1, I have an asymptote. So the function, as x goes to -1, the function goes to infinity. We determined that when we looked at the terminal behavior. So this is fine. And how about on the right side of 0? On the right side of 0, we know that the function increases, right? And it is concave up, right? Increases, concave up. So how would it look like? And we know that as x goes to infinity, the value of the function goes to infinity as well, right? Am I making sense? Is everybody okay? Now, in order to be more precise, you have to pick your scales precisely and plot some more points. So if you plot some more points here, or some arbitrary points like at 1, at 2, at 3, you'll get a little bit better sketch. But this is fine, okay? As long as you this is the overall shape of the curve, okay? This is I have the asymptotes and everything, all the information is there. Yeah. Can you what? I don't know how to open the windows. I don't think you can. You can pull the blinds.
Yes.
Yeah, so I don't think you could do that, okay? All right, so that's it. That's the graph. I have all these steps there. Now, like I said, I have a take-home quiz here, okay? And you have to basically follow the same steps that as I did in the class and sketch the graph of this function that I have here, okay? And I already gave you the homework on section 3.5 and 3.7, so you have to look at them. Does anyone have any questions for me? Anyone has any questions? Now, I do want to do one more example from this section. However, I want to finish up section 3.7 first and see if I have time to do that. Okay? So I'm going to go ahead and I'm not going to do anything from 3.5 anymore. Everything in 3.5 is basically you follow the same steps. Okay? But I want to do one more example using sketching the graph of a function involving the trig functions. Okay. So I will do that either today if I have time after 3.7 or tomorrow. Somebody hates trig functions. But trig functions have a lot of applications in engineering, right? Yeah. Okay, so I am going to go ahead and go into section 3.7. As I said, we are skipping 3.6. 3.6 is really something that you could do on your own. 3.6 is on sketching curves as well. Yeah, so in 3.6 you also need to use your calculator and so on. So I'm not going to go over that. Okay, section 3.7 is on optimization. Section 3.7. This is on optimization. And basically these are again word problems like we have done in the related rates section. And I'm going to explain how to deal with these problems by going through a number of examples. So my first example would be the following. Here's my let's say a farmer has 2,400 feet of fencing, and wants to fence off a rectangular field that borders a straight river. And you don't need any fencing on the side of the river. The question is, what are the dimensions of the field that has that has the largest area. Okay, so that's the question. You have a farmer. The farmer has 2,400 feet of fencing. So that's his restriction on resources. That's the limited resources that he has, and he wants to fence off a rectangular field by the river. On the side of the river, he doesn't need any fencing. And the question is, how should he pick the dimensions to have the maximum possible area? Am I making sense? In all these problems, you have limited resources and you want to maximize or minimize something given that limited resources. Am I making sense? So in this case, the amount of fencing you have is limited. You only have 2,400 feet of fencing, and you want to pick the dimensions of the rectangle in any way so that you have the maximum possible area. You want to maximize the area inside the field. Okay, so pick dimensions in a way that maximizes your area. Am I making sense? So what's the maximum possible field you can make by using 2,400 feet of fencing? Okay, is everybody clear on the question? Okay. Now, in order to understand the question, it is desirable to make a diagram if possible. So I'm going to make a diagram here. So let's say that's the rectangular field. Let's say the river is on this side. So this is the river side. And on the river side, you don't require any fencing. The fencing is only required on the solid sides of the rectangle. And was that? Yeah, I'm gonna get there. Yeah. So after I draw my diagram, I know that I have a rectangular field, and we are talking about maximizing the area of the field, right? So. And we know that the area depends on the dimensions of the field. So we have to label the dimensions. Okay. So let's say that this side, let's call that X. Let me see which one I want to call X. Yeah. Let me call this side to be X and this side to be Y. Okay, and then what would be the other side? X as well, right? Okay, so that's my, so I draw a diagram first, and then I label or denote the dimensions by X and Y, okay? And then I ask myself, what am I trying to maximize or minimize? Well, in this case, I am trying to maximize what? In this case, I'm trying to maximize area. So then, I need to know what is the area. Well, in this case, the area, I'm going to denote the area by A. So A will denote the area of the field. Now, can someone tell me what is area? What does area equal to? X times Y. So we need to figure out how we should pick X and Y in order to maximize this function, right? So what is our goal then? Our goal is maximize maximize the area subject to what? So what's the restriction though? If I can pick any dimension I want, then I can make area to be anything I want. So, but there is a restriction, right? There is a limit. There is we have limited resources. So what's the we want to maximize subject to what restriction? Subject to the fact that the total I have 2,400 feet of fencing, right? So what's the total length of the sides? So the total perimeter of the field where I need fencing would be what? Y plus 2x. That's the total perimeter of the sides where I need fencing, right? And that has to be equal to what? 2,400. Okay. So I have to maximize the area subject to this restriction. Okay. Now the area is expressed in terms of two variables, right? X and Y. In calculus 1, we don't know how to deal with a function depending on two variables, right? So we can only deal with one variable function. So the first step would be to express the quantity that you are trying to maximize or minimize. You have to express it in terms of one variable only. Okay. So can I do that here? Yeah. All I have to do is use the equation y plus 2x equals to 2,400, and we can solve for y there, right? So if I solve for y, what do I get? If I solve for y, I get 2,400 minus 2x. And then I'm going to plug that in for y in the formula for a. So I get a would be x multiplied with 2,400 minus 2x. And what does that equal to? Yeah, so a would be equal to 2,400 x minus 2x squared. Is everybody okay so far? So we have expressed our area function in terms of the dimension x only. Now I have to be, so I want to find then the maximum value of this area function, right? But the maximum value of this area function on what domain? I have to now understand on what domain. Okay, so what are the possible values of x that I can pick? That's the question. Okay, so notice that, so how do I come up with that? Let me maybe do it here. Notice that, I guess you would agree with me that x has to be non-negative, right? It's a length. It's a length. At the same time, you can see that y has to be non-negative, right? Y has to be non-negative. You agree with that? Well, the length is not negative. Yeah. So, but we expressed y in terms of x as what? Y is the same as 2,400 minus 2x, right? So that also tells you that this has to be non-negative. And from there, if I solve for x, what do I get? This says negative 2x is larger than what? Negative 2,400, right? And then x is less than or equal to what? 1,200. So notice that this condition tells me that x is non-negative, and then this condition tells me that x cannot exceed 1,200, which makes sense because if you pick x to be 1,200, right, If you pick x to be 1200, then your field is what? The width of your field, y is 0 then, right? Because if you pick x to be 1200, so on this side 1200, this side 1200, 2400 of fencing, but then your y would be 0, right? So your area would be 0. So that's the maximum value of x you can pick. If you pick x bigger than that, y becomes negative, right? So then I see that I have to find maximum of A, which is 2400 x minus 2x squared on the domain, or let me say for x between 0 and 1200. So the entire problem now is to find the maximum value. So I have to find the value of x where the maximum of area occurs, right? I have to find the value of x where the maximum of area occurs, which is a problem that we should know now, right? I have a continuous function a on a closed bounded interval from 0 to 1200. Do I know how to find the maximum of that function? Remember last time I did one example where I found, was that? Well, you want to find the critical points, and we know that the maximum or the minimum can occur only at the endpoints or at the critical points, right? That's the problem that I'm referring to. So how do I find this maximum? Well, I find the area, the derivative of the area. So, when I am finding out the possible values of x, right? The restriction that I have 2400 feet of fencing, that restriction is telling me mathematically that the value of x can only be between 0 and 1200. Okay, that's my reality check of the problem. That x cannot be anything. It has to be between 0 and 1200. So with that restriction that x has to be between 0 and 1200, what's the maximum value of the area? To find that, I have to find the derivative first. So what's the derivative of a at x? Well, that's going to be what? 2400 minus 4x. And in order to find the critical point, I have to set that equal to 0 and solve for x, right? So then I get what? I get 4x is equal to 2400. What's that? Oh, I can say negative and negative here. And then x has to be what? X has to be 600. Now, I know I have only one critical point, right? There is only one critical point here. I know that if I have a continuous function on a closed bounded interval, then the maximum and absolute max, absolute mean occurs either at the endpoints or at the critical points, right? Now, there are only one critical point. Can the maximum occur at the endpoints in this case? Well, think about it. If x is 0, that means my width is 0. Then the area would be 0. That cannot be the maximum area. If x is 1200, then my y value length is 0. Again, area would be 0. So that cannot be where the maximum occurs. So now I don't even have to compute the value of the area at the. So usually what do I do? I evaluate the area function at 0. I evaluate the area function at 1200. I evaluate the area function at 600. But in this case, it's pretty clear that the maximum will occur at 600, right? So usually, let me just say, usually you would calculate an area like this, a table like this. At the endpoints, the area is clearly 0. And when x is 600, area is something which is positive. I don't even have to calculate that, unless the question says find the maximum area. Well, let's calculate that. What's the maximum area? I have the area function, right? So in the area function, if I replace x by 600, what do I get? Can someone tell me what that is? If I in the area function, if I replace x by 600, what do I get? 0. In the area function right here, if I replace x by 6, was that 720,000? Okay, 720,000. So that's the maximum area. So this is where the maximum occurs. Now, so we got that x is 600. Then, what should be y then? What should be y? Yes, y. Everybody says how y is 1200. Remember, y was 2400 minus 2x, right? So if I replace x by 600, then I get 1200 here. So what's my final answer? Final answer is that I remember the question was how you should choose the dimensions to obtain the maximum possible area. So the dimensions that I need to pick are x is 600, y is 1200. Are we okay with what I just said? Anyone has any questions? Anyone has any questions? Yeah. Yes. Did that make sense to you, all of you? Okay, let's take a break for 5 minutes, and when we come back, I'll be going over more problems like this. Yeah, we are still in 3.7, okay? If you are taking somebody else's exam, you have to let me know whose exam you are taking, okay? Okay, this problem is asking us for the following. We have a cylindrical can. We have to make this cylindrical can to hold 1 liter of oil, and we are asked to find the dimensions of the can that will minimize the cost of the metal to manufacture the can. Okay, so how can we make the can? So the question is, how do you choose the dimensions of the can to minimize the cost of producing the can? Okay, so here we are given the cost of metal is, let's say, the same, is constant, so it doesn't change. So what is it really asking us to do? How would I minimize the cost of manufacturing the can? So what am I trying to minimize here? Pretty good. If I want to minimize the cost of producing the can, what I need to do is I need to make sure that I'm minimizing this total surface area that I need. Okay? Is everybody clear on that? If I want to minimize the cost of metal to produce the can, that would mean that I want to use as less metal as I can. So my metal will be used to make the surface of the can, right? The metal would be used to make the surface of the can. The surface, top, bottom, the side, all of it. Is everybody clear on that? So to minimize the cost here means to minimize the surface area, because if I minimize the surface area, then I'm minimizing the amount of metal that I need to use for each can. Is that making sense? Okay, so again, make a diagram if you can. So let's make a diagram here. We are talking about a cylindrical can, right? So let's make a cylinder. Let's say, let me make it the cylinder first. So a cylinder has it's a circular cylinder. So the top is a disc or a circle. The bottom is a disc as well. Okay. Let's denote so what are the dimensions of a cylinder? Well, it's the radius of the bottom or the top and the height. Those are the two dimensions. So let's label the radius by R. So R is the radius of the cylinder. In other words, is the radius of the bottom. And we are going to label the height by H. Okay, so let's say H is going to denote the height. Okay. In the question, what is the restriction? We are trying to minimize the surface area, subject to what? Subject to the fact that it has to hold 1 liter, right? And that would mean that inside the cylinder, the volume needs to be 1 liter. So so first of all, notice that what is the surface area? So S will denote surface area. S will denote surface area. And let's let V to denote volume. Okay. What is my goal then? Goal is minimize surface area subject to what? Subject to the condition that the volume has to be what? 1 liter means, in terms of cc, is what? It's 1,000 cc, right? Is everybody okay? Or I mean centimeter cube, right? When I say that, 1 liter means 1,000 centimeter cubed. So with this condition, I want to minimize the surface area. So I need to express the surface area as a function of the dimensions, okay? Because the question is, how do I pick the dimensions so that the surface area is minimum possible? So I need to express surface area in terms of the dimensions. So what is the surface area in terms of the dimensions? Well, first of all, what are the areas of the top and bottom? Pi r squared. So I have 2 pi r squared for the total area of the top and the bottom. So what's the total area of the top and the bottom? The top and the bottom each has area pi r squared, because each one is a disk of radius r, and then you have to multiply by 2 because you're talking about the top and the bottom, both of them. So the total area of the top and the bottom is given by this. You agree with that? Now I need to know what's the area of the side of the can. How would you answer that? Yeah. Yes. So imagine that you have the can, right? And imagine that whatever the can is, you cut the can vertically like this, and then you open it up, and what you're going to get is a rectangle. So if you whatever the can is, if you cut the can along some side, you cut the can along a straight line like this, and then you open it up, what you get is that you get a rectangle, and the rectangle that you get, one side has length 2 pi rh, sorry, 2 pi r. That's the length of one side, because that's the circumference, right? The circle, when you spread it, right, open it up, the circle will become straight line. So the circumference of the circle will be one side, and the other side would be the height of the can. So the area of the side is given by the area of this rectangle, and the area of this rectangle is what? 2 pi r times h, as you said. Is everybody okay? So that's the surface area. And again, the surface area is given in terms of 2 variables, the radius and the height, and we have to express it in terms of 1 variable only. How would I do that? Well, we are given that the volume is 1,000 centimeter cubed. What's the volume of a cylinder? The volume of a cylinder is the area of the bottom multiplied by the height. So the area of the bottom is pi r squared, and you multiply that by the height. That's the volume. And we need the volume to be 1,000 centimeter cubed. Okay? 1,000 cc. Now, from here, can I solve for h? H is what? 1,000 divided by pi r squared. Everybody is okay with that? Okay, I am going to keep that in. I'm going to highlight that because you're going to need that later. Now I want to express my surface area in terms of the radius only. In terms of 1 variable, I picked the radius. Okay, you could pick h if you wanted to, but it's easier to use a radius in this case. So the surface area as a function of r can be expressed as what? 2 pi r squared. I don't have to do anything with that. But then I have 2 pi r multiplied by h, right? And instead of h, I am going to write what? 1000 divided by pi r squared. Okay, so let's simplify that a bit. I get 2 pi r squared plus pi cancels out, and 2 times 1000 would be 2000, right? And r cancels out, but so I have only 1 r, right? So like this. Now I have to do a reality check. I cannot pick the radius to be whatever I want, right? If I could pick the radius to be whatever I want, then we wouldn't be asking this question. So what are the possible values of the radius? Can somebody answer that question? What can I pick for the radius? The only condition that I have here, right? The only condition that I have, so, well, let me write that down first. So I am trying to minimize, so my goal now is to minimize, S of r subject to the condition that the volume is 1000 cc. And we know that the volume is, this condition simply means I have pi r squared h is 1000, right? Is everybody okay? So subject to the condition that pi r squared h is 1000, I have to minimize the surface area. So my question is, what are the possible values of r? Let's see if we can figure that out. Well, r has to be non-negative, right? Well, r has to be, in fact, positive. Why can it not be 0? If it is 0, then the volume would be 0, but we want the volume to be 1 liter, right? So it cannot be negative because it's the length. It cannot be 0 because otherwise the volume would be 0. So it has to be positive. My question to you, can it be any positive value? Can r be any positive value? Why is that? Well, I would argue differently. I would argue that r could be any positive value. You might say why? Well, if I pick r to be whatever I want, I can pick r to be 1 million centimeter, so I'm going to have a really fat cylinder, but then the height would be very, very tiny, right? So notice that, so if I pick r to be 1 million centimeter, then h would be calculated according to this formula here. Okay. Well, then h would be very, very tiny, right? But still, the volume would be 1 liter. Am I making sense? So I can pick r to be anything I want as long as it's positive. If I pick r to be very tiny, like 0.1 centimeter, let's say, that would mean that I have a really narrow cylinder, but the height is very long. It's a very long cylinder. Am I making sense? Okay, so then you agree with me that our goal now is to find minimum value of the surface area, which is given by 2 pi r squared plus 2000 divided by r, for subject to the condition that r is non-negative. Sorry, r is positive. Okay? And that's an infinite interval, right? That's an infinite interval. That's not a finite interval, right? In the previous problem, I had finite interval. So what I did is I found the critical points, I evaluated the function at the endpoints, at the critical points, and that told me what was the absolute max in that case. But here, I have an infinite interval. R is from 0 to infinity, okay? Well, what do I do in this case? Well, we know exactly what to do. If I find out where this function is increasing and decreasing, that's going to tell me exactly where the minimum is, right? So let's see. Let's find the critical point first. So what's the critical point? What's the derivative? What's the derivative? Anybody? Well, what's the derivative of the first term? That's going to be 4 pi r, right? You agree with that? 2 pi times 2r? That's the derivative with respect to r, or the first term. What's the derivative of the second term? I have 2000 divided by r, right? Yeah, everybody agrees with that. What's the derivative of 2000 divided by r? Let me do a scratch work here. So we are trying to take the derivative of 2000 divided by r. You could apply the power. You could apply the quotient rule if you want, but you can write this as what? 2000 times r to the negative 1, right? So what's the derivative? The derivative would be 2000 times negative r to the negative what? 2, which is the same as negative 2000 divided by r squared, right? Because r to the negative 2 is 1 over r squared. So he's right. What we get is 2000 divided by r squared. Very good. So that's the derivative. Now I have to find the critical point, so I have to solve s prime of r equals to 0, which would mean that 4 pi r minus 2000 over r squared is 0. Multiply everything by r squared, what do you get? 4 pi r cubed minus 2000 is equal to 0. So then I get 4 pi r cubed is 2000. R cubed would be 2000 divided by 4 pi. What is that equal to? 4 goes, okay, so this is 500 over pi, right? And so r would be the cubic root of 500 divided by pi. And if you have a calculator, you can calculate approximately what that is. So the point though is I have only one critical point, right? All I have is only one critical point. Is everybody okay? Now, if the function has a minimum, it's gotta occur at that point, right? It's gotta occur at that point. But let's check. Remember, the r value could be anything from 0 to infinity. So r value could be from anything from 0 to infinity. So that's the domain of the function surface area. And the only critical point that I got is at the point where? 5.42. That's 5.42?
Yeah.
So this is the only critical point I have, and which is about 5.42. Now the surface area function, the derivative function, is it positive or negative on the left side of the critical point? The derivative function is given by this, right? Is it positive or negative on the left side of the critical point. The critical point was about 5.42, right? So what can you plug in? You can plug in 1. If you plug in 1, you definitely get what? The derivative S prime, right? S prime is negative here, right? And beyond 5.42, you can plug in 6, for example, or 7 or 10. And if you plug that in, let's plug in 10 because it's easy, right? If I plug in 10, it's definitely positive, right? Because 2000 divided by 10 squared, which would be 2000 divided by 100, which would be 20. And then when you plug in 10 for R here, you get 4 times that, 40. So it's clearly positive. So the derivative is indeed positive here. What does it tell you? It tells you that my function, the surface area function, is decreasing here, increasing here, right? Where is the absolute minimum? At the critical point, right? So the absolute minimum occurs here. Okay. So then we know that S surface area evaluated at this number 500 divided by pi, cube root of that. This is the minimum. This is the absolute minimum. And so how should we pick our dimensions? Well, we should pick the radius to be 500 over pi, cube root of that. And if that's radius, what is height? What is height? Well, we expressed height in terms of radius before, right? Right here. Height is 1000 over pi r squared, right? So if I replace r by 500 over pi cube root of that, I can get what h is, right? Okay, so what do I get? H would be 1000 divided by, what do I have there? 1000 over pi r squared, right? Pi times r squared. So instead of r, I need to have 500 over pi cube root of that squared. So that would be my height. Again, use your calculator. So this is about 5.4, somebody told me, and I think that's the right number. And what is the height? If you don't have your calculator, you can leave your answer this way, but height is what about? Anyone has that number? Instead of cube root of 500, you can write down 5.42 now, right? So it's basically 1000 divided by pi times 5.42 squared. Doesn't sound right, because if you have 10 and 5, then the volume, it doesn't become 1000, right? Can someone else do that calculation also? Was that 43? Yeah. Was that 1000 divided by pi times 5.42 squared, right? Maybe that's the right number. Let's check. If I get 10 and 5, am I getting volume to be 1000? So what is pi r squared times h then? If I take h to be 10 point, what you said, and r to be 5.4, then is the volume close to 1000? So what is pi r? So calculate pi r squared times h. So calculate, what I'm saying, calculate pi times 5.42 squared times h to be whatever you're saying, 10 point what? 4 you said? Am I getting about 10 point what? 83? Am I getting about 1,000 there? Okay, then your answer is correct. Okay. So I am getting H to be about 10.83. I don't know why I wrote 558 before, okay? So that's why I kept saying maybe it's not the right number. So I have a mistake in my notes here. It should be 10.83. Okay. So my final answer then is what? My final answer is that I should pick the dimensions as R is 5.42 and H is 10.83 in order to minimize the surface area. So if I minimize the surface area, I minimize the cost as well. Okay, is everybody okay with what we did? Any questions so far? So that was the second problem. Everybody's doing okay with this. Okay, what time is it? 11:54. Okay. Now, I do want to do more examples, but let me do the examples. So tomorrow, I'm going to begin with an example from 3.5 and an example from 3.7, okay? And in the meantime, I hope that you are going to try the homework problems and see if you get stuck with any problems. So that's what I'm going to do tomorrow. But I am going to shift gear here and go to 3.9, okay? 3.9. So don't be anxious. I'll do more examples from 3.5 and 3.7 tomorrow. But I do want to get into 3.9. The reason is I am a bit anxious about finishing up the syllabus, okay? So I want to make sure that I finish up 3.9 and then I can relax a bit. Was that? This is the last section in chapter 3. We have to finish up chapter 4 at the list before the final. Yeah. But we are in a good position once I finish this, okay? So I don't have to rush too much if I finish this. Okay, so this is on antiderivatives. This is on antiderivatives. So what I'm going to do is start with the definition. A function capital F of x is called an antiderivative. Is called an antiderivative of f of lowercase f on an interval I if the derivative of capital F is equal to the lowercase f for all x inside of I. Is everybody okay? So basically, capital F is the antiderivative of the lowercase f if the derivative of f is lowercase f. Okay? Now lowercase f is the derivative of uppercase f, right? Derivative of f is the lowercase f is the derivative of the uppercase f, and the uppercase f is the antiderivative of the lowercase f, right? Am I making sense? What's that? What I'm saying is lowercase f is the derivative of uppercase f, and uppercase f is the antiderivative of lowercase f, right? The opposite. Yeah. So we are going to use the term differentiation, right? Differentiation is the term the term we use for taking derivative. Anti-differentiation would be the term for finding the antiderivative of a function. Okay. Let me give you an example. If I have the lowercase f of x function to be half of if I take the function x, and if I take the uppercase f of x to be half of x squared, then notice that the derivative of the uppercase f is exactly the lowercase f, right? Is everybody okay? So then capital F is an antiderivative. You know what? Let me just say this for the following. So what we say is that half of x squared is an antiderivative of the function x. Okay. You would also agree with me that if I say that half of x squared minus 1, is it an antiderivative of x as well? Because if I take the derivative of half of x squared minus 1, I still get x. Same way, if I take the derivative of half of x squared plus 3, I still get an antiderivative of x. Now you would realize that if I add any constant to half of x squared, that's an antiderivative of x, right? So the question is, are they the only antiderivatives of x? If I am trying to find the antiderivative of x, are these the only antiderivatives of x? Notice that if I give you a function, it has only one derivative, right? But if I give you a function, if I ask you to find the antiderivative, it may have many antiderivatives, right? Like the function x has antiderivatives, each one looking like this, right? C could be any constant here, 1, 2, 3, 4, negative, pi, whatever you want. So a function has many antiderivatives, right? Okay. Now the question, are they the only ones? Are they the only antiderivatives of x? And the answer is yes. Once I find the antiderivative half of x squared, half of x squared is that's the simplest antiderivative of x. Once I find that, all the other antiderivatives can be found by adding a constant. Okay. And how do I know that? Because when we talked about mean value theorem, I gave you a theorem which says the following. If capital F of x and capital G of x are both antiderivatives of lowercase f, then they differ only by a constant. Then g of x is f of x plus c for some constant c. Okay, in section 3.2, when we talked about mean value theorem, remember I gave you the mean value theorem as an application of that. I said if capital F prime and capital G prime are equal, so in this case f and g, both of them are antiderivatives of lowercase f, right? So what does that mean? Doesn't it simply mean that the derivative of f, capital F, and the derivative of the uppercase G, they are both equal to f of x, right? That's what it means. So in 3.2 I said if two functions, they have the same derivative, they differ by a constant only. If two functions have the same derivative, they differ by a constant only. That's what I said in 3.2. And that's exactly what we are saying here, right? So if uppercase f and uppercase g, they are both antiderivatives of the same function f, then they differ only by a constant. So that's how I know. If I ask you to find a antiderivative, all the antiderivatives of a function, all you have to do is find one, and then you know that all the other ones are you just have to add a constant to find all the other ones, right? Okay, so we are going to use the following notation. So in the example that I had, we said that half of x squared is an antiderivative of x, and I'm going to say that half of x squared plus c is the general antiderivative of x. Okay, so when I say general, that's the general form of all the antiderivatives, right? Every antiderivative of x is half of x squared plus a constant. So I'm going to call half of x squared plus c the general antiderivative of x. Okay, because it represents all the antiderivatives. And we are going to use the notation. This notation will mean that I'm taking the antiderivative of x with respect to x, and this is equal to half of x squared plus c. Okay? So this is called the antiderivative. Okay? So the way it is pronounced is, this is called the indefinite integral of x with respect to x, yes. Okay. So this is this guy here. That's the guy I have here, and this is called the integrand. So basically, the indefinite integral of a function is the general antiderivative of that function. Indefinite integral of a function is the general antiderivative of that function. Is everybody okay with what I said? Everybody's okay with the notation? Okay. All right. Let's do another example. If I ask you, what's the indefinite integral of let's say 3x squared. What's the indefinite integral of 3x squared with respect to x? What would you say? You're trying to find the general antiderivative of 3x squared, right? So you're trying to find a function whose derivative is 3x squared. Find a function whose derivative is the integrand 3x squared. What is that? X cubed. The derivative of that is 3x squared, and then you add a constant to it. You get the general antiderivative of this function 3x squared. Is everybody doing okay with that? Okay. Let's look at the power rule for indefinite integrals. So this is we had a power rule for derivatives. We also have a power rule for indefinite integral. What is that? It is the following: for any real number r not equal to -1, the indefinite integral of x to the r is equal to 1 over r plus 1 x to the r plus 1 plus a c. So, I forgot to write dx here. So the indefinite integral of x to the r is given by this. What's the proof of this? Well, what's the derivative with respect to x of x to the r? Sorry, x to the I want to say the derivative of the right hand side. So So what's the derivative of 1 over r plus 1 times x to the r plus 1? What is the derivative of that? By using the power rule for derivatives, the derivative is what? The constant 1 over r plus 1 times the derivative of x to the r plus 1 is what? R plus 1 times x to the r, right? Which is just x to the r. Is everybody okay with that? Now, this is as long as r is not -1, right? Right? What's the problem when r is -1?
You got a negative, you got a 0 non-equal. So it doesn't work. The formula doesn't work
if r is -1. That's why we are omitting
the case r is -1. So you might say, well, what happens when r is -1? What's the indefinite integral of x to the -1? Okay, and the answer, you have to wait till we go to calculus. I don't want to
destroy what you're going to see there, but just, you're going to see there. It's basically the natural log of x. You're going to see that when you go there. Okay, so so the indefinite integral of actually -1 is not something we know right now. Okay, so you're going to see that when you go to Calc 2. Okay, otherwise we can find the indefinite integral of any other power of x. Okay, except for the exponent -1. So example, what's the indefinite integral of x to the 4 dx? Well, by my power rule, it will be 1 over 4 plus 1 times x to the 4 plus 1 plus the c, and which is what? 1/5 x to the 5 plus c, right? Is everybody okay with that? I'm using the power rule. The power rule is in front of you. The indefinite integral of x to the r dx is 1 over r plus 1, x to the r plus 1 plus c. So here, in my example, r is 4. So indefinite integral of x to the 4 will be 4 plus 1, x to the 4 plus 1 plus c. Okay, so we are using that power rule. Any other questions on this example? Everybody is doing okay? Now remember, if I have a sum of functions, I can take the derivative term by term, right? Also, if I have to find the derivative of a constant multiple of a function, I can take out the constant, right? Those properties also hold for integrals, indefinite integrals. So here are some algebraic properties of the indefinite integrals. And without even trying to write down any conditions, I'm just going to write down the formulas. So if I take the indefinite integral of f of x plus or minus g of x, so I'm taking the antiderivative or indefinite integral of a sum of functions, then I can take the indefinite integral term by term. Okay, term by term. Like this. And the second one, the indefinite integral of a constant multiple of a function f of x. So here c is a constant. Then I can take the c outside of the indefinite integral, and then I get c times the integral of f of x dx. Okay. How are they helpful? Well, now using the power rule together with these two rules will allow me to integrate any polynomial functions. Okay. So here is my here's the example. Let's say I need to find the integral of 2x cubed minus 5x plus 3. And so I'm going to apply the previous theorem. I know that if I have a sum of functions, I can take the integral term by term. 2x cubed dx minus the integral of 5x dx plus the integral of 3 dx, which is the same as, now I can apply number 2 of the theorem. I can take out the 2. I get the integral of x cubed dx minus 5 times the integral of x dx plus 3 times the integral of 1 times dx. Okay. What's the integral of x cubed? By the power rule, it is what? 1 over 4 x to the 4, right? Minus, what's the power rule formula for integral of x? 5 times half x squared, right? Okay. And then the last one would be what? The derivative of x is 1, right? So this is 3x. And I'm going to write a c altogether at the end. Okay, you don't have to write a c for each integral. If you write a c1 for this, c2 for this, c3 for this, then c1 plus c2 plus c3 altogether is written as a c. Okay, so you just write a c at the end. Any questions on this? Well, I have the integral of this polynomial. So my previous theorem says I can integrate term by term. So I integrate one term at a time. So
Integrate integral of the first term, integral of the second term, integral of the third term. Now in the previous theorem said if I have a constant factor here, that constant factor can be taken outside. So 2 goes outside, 5 goes outside, 3 times 1 here, so I can write 3 times the integral of 1. Now the power rule says you add 1 to the exponent and divide by that. So x to the 4 plus 1 divided by 4. Sorry, x to the 3 plus 1 divided by 3 plus 1. X to the 1 plus 1 divided by 1 plus 1. Right, that's what the power rule is. And here, the integral of 1 is just x because the derivative of x is 1. Is that making sense?
Okay. Notice, okay, so if you can go from the first line to the final line, the last line, if you could do that, that's okay. In fact, I would like to see that. If you go from the first line to the last line, that would be fine. Let me do one more example here. What's the integral of negative x squared plus 5x plus 2? Well, this would be the integral of negative x squared dx plus the integral of 5x dx plus the integral of 2 dx. This is equal to negative the integral of x squared dx plus 5 times the integral of x dx plus 2 times the integral of 1 dx. Okay, so this is equal to negative, by the power rule I get x cubed divided by 3 plus 5 times x squared divided by 2 plus 2 times x, and at the end I add a constant c. Okay? Is everybody doing okay? The last step? Yeah, we are using the power rule, right? The power rule says
the integral of x to the r is x to the r plus 1 divided by r plus 1. Right? So if r is 2, you get 2 plus 1, 2 plus 1 here, right? So x cubed over 3. So the power rule for derivative, you take down the exponent, you subtract the exponent by 1, right? Here, you increase the exponent by 1 and then divide by the same exponent. Okay?
everybody's okay with that? Next example. We are going to make it a little bit more difficult. What's the integral of root x plus 1 over root x dx? Well, again, this is basically having x to the half plus x to the negative half, right? You agree with that?
Yeah.
So I am going, so far I only know how to use the power rule to find indefinite integrals. So you have to write everything as powers of x. And then this is the integral of x to the half plus the integral of x to the negative half. Now if I apply the power rule, what I get is I get x to the half plus 1, and then I also have to divide by half plus 1. Okay, plus 1 over negative half plus 1, x to the negative half plus 1, and then I'm going to add a c. What do I have then? 1 over 3 half here, right? X to the 3 half plus 1 over a half here x to the half. Notice that 1 over 3 half is 2/3. X to the 3 half plus a 2 x to the half plus a c. Is everybody okay with that? Okay, so that's the final answer. Everybody's done writing it down? Everybody's done with that? I'm just going to do one more example here. Example, what's the integral of t squared plus t plus 2 divided by root of t? What would I do here? In this case, again, the only thing I know so far is the power rule, so try to write everything in terms of powers of t. So you're going to write this as t squared over root of t plus t over root of t plus 2 over root of t. And then, what is root of t? Root of t is 2 to the power half. So what is t squared divided by t to the half? This would be t to the 2 minus a half, right? Plus this would be t to the 1 minus a half. Plus this would be 2 times t to the negative half, right? No, I'm not taking derivative. I'm writing t squared divided by root of t. That's the same as, so t squared divided by root of t, right? That's the same as t squared divided by t to the half, right? So you subtract the exponents, right? So you get this. So this is equal to the integral of t to the 3 half, right? Plus t to the half plus 2t to the negative half. Okay, now you take the integral of each one. What's the integral of t to the 3 half? It's going to be t to the 3 half plus 1 divided by 3 half plus 1 plus t to the half plus 1 divided by half plus 1. Here you're going to get 2 times t to the negative half plus 1 over negative half plus 1 plus the c at the end. Simplify a little bit, you get, in the denominator, what do you get? T to the 5 half divided by 5 half plus t to the 3 half over 3 half plus 2 times t to the half over a half plus a c. So this would be 2/5 t to the 5 half plus 2/3 t to the 3 half plus, what would be that? 4 t to the half plus a c. Is everybody okay with that? Everybody is doing okay with that? Any questions on that problem? If I ask you what's the integral of cosine x, what would you say? Yeah, because the derivative of sine x is cosine, so the integral of cosine would be sine. What would be the integral of sine x? Negative cosine x, right? So let me write that down. So remember that the derivative with respect to x of cosine x is negative sine x, right? Negative sine x. So that implies that the indefinite integral of sine x is negative cosine x plus c. And same way, what's the integral of cosine x dx? Integral of cosine x dx would be sine x. Can someone tell me what's the integral of secant squared x? The derivative of tangent, the derivative of tangent is secant squared. So the integral of secant squared would be tangent. What is the integral of cosecant squared? The derivative of cotangent is negative cosecant squared. So the integral of cosecant squared would be negative cotangent. What is the integral of secant times tangent? Integral of secant times tangent is secant, because the derivative of secant is secant times tangent, so the integral of secant tangent would be secant. What is the integral of cosecant cotangent? Negative cosecant, right? You have to have them memorized, okay? And when you need to use them, they have to be at the top of your fingers. Like you don't have to think about it, okay? Just you have to know them by heart. Before I let you go, sometimes you see things like this. What's the integral of cosine 5x? Can someone find an antiderivative of this guy? What is the antiderivative of cosine 5x? Well, you know that it has to be something like sine 5x, right? However, what's the derivative of sine 5x? The derivative of sine 5x, the derivative of sine 5x, yeah, cosine what? Is cosine 5x multiplied by what? Multiplied by 5, because it is sine of 5x. You have to apply the chain rule, right? Sine of 5x. So the derivative would be cosine 5x multiplied by 5, right? The derivative of the inside is 5. So the derivative of sine 5x is not exactly cosine 5x. So how do I make it exactly cosine 5x? If I have 1/5 here, then I'm going to get a 1/5 here, and now I have exactly cosine 5x, right? So that means the indefinite integral of cosine 5x is 1/5 sine 5x plus the c. Is that making sense to you? If you take the derivative of 1/5 sine 5x, then you get exactly cosine 5x. Is everybody okay with that? Generally speaking, if I have cosine of any constant a multiplied by x dx, it's going to be 1 over a times sine of ax plus c, as long as a is not 0. As long as a is not 0. Of course, if a is 0, then it's just a constant function there, right? Cosine 0 is 1. So as long as a is not 0, you have that. Okay? Can someone tell me what would be the integral of sine ax? Sine ax. Can you guess what that is? Negative 1 over a cosine ax plus c. Okay, I'll just stop right here.